Hey there, it's Shannon Myers, and today we'll be looking at graphs, definition and basic properties, and this is for our discrete class. So here we go. Definition: a graph, G, consists of two finite sets, a non-empty set V at G of vertices and a set E at G of edges, where each edge is associated with a set consisting of either one or two vertices, called its endpoints. The correspondence from edges to endpoints is called the edge endpoint function. An edge with just one endpoint is called a loop, and two or more distinct edges with the same set of endpoints are said to be parallel. An edge is said to connect its endpoints. Two vertices that are connected by an edge are called adjacent. And a vertex that is the endpoint of a loop is said to be adjacent to itself. All right, and the last part of this definition is an edge is said to be incident on each of its endpoints, and two edges incident on the same endpoint are called adjacent. A vertex on which no edges are incident is called isolated. Okay, so let's try to put all this together as an example. So please draw a picture of the specified graph. So this graph H has a vertex set, V1, V2, V3, V4, and V5, and edge set, E1, E2, E3, and E4, with the edge endpoint function as follows in this chart here. So this kind of gives us a map, if you will, of how to draw our graph. So here, going through sort of one by one, we know for sure we're going to have 5 vertices, right? And by the way, there's more than one way to draw this graph, probably infinitely many ways. So we can draw it a couple different ways and check it out. So here, I'm going to go ahead and we'll do our vertices, I don't know, in a different color just to make it look different. I'm going to just say 1, 2, 3, 4, 5. So if I have something like that, where I have V1, V2, V3, V4, and V5. That is my set of vertices. And now let's take a look. So here, the edge E1 just has one endpoint. So that means that V1 is going to be adjacent to itself, right? And E1 is incident on V1. So we need to draw a loop for that one. So we'll do our loop, I don't know, purple, I guess. And it'll look something like this. Cool so far? All right. So now let's take a look. So we've taken care of this first one. So edge 2 is incident on V2 and V3. So let's look at V2 and V3, and we can just draw either a straight line, or we can draw kind of a loop, or not a loop, sorry, a curve. So if we do something like that, we can call this one as E1. We should name this as E2. And then E3 is an incident on V2 and V3 as well. So here, this one here we could call E3. And then E4 does what? It's incident on V1 and V5. So we can either, you can draw it curved or you can draw it straight. And so here we have E4. Cool so far? So notice that the vertex V4 is isolated, right? And let's take a look at just some notes about this. You're going to learn about connected graphs. This graph is not connected, even though we could draw this differently, right? If I kind of play around with this, we could move this, and we could draw it where it went something like, something like this. I'll move it back, but we could draw it something like that, and it would look like it was connected. But notice that there's no vertices that are on those parts of E2 and E3 that edge E4 seems to intersect. So I'm going to just go ahead and move it back here, but you could redraw this graph something like that, and you would see that it would be still considered to be not connected. All right. So anyway, just a few observations, a few notes, if you will. All right. So one note is that if we look for any parallel edges, are there any parallel edges? What was that definition? Two or more distinct edges with the same set of endpoints are parallel. So do you see that happens with E2 and E3? They both have the same set of endpoints and they are distinct, right? So E2 and E3 are parallel. And we've said some of these things in words, or verbally. And just an example of the incident language, E1 and E4 are incident on V1. And if you look back on incident, it's an edge is said to be incident on each of its endpoints. Okay, so E4 would also be incident on good V5. All right, and then if we keep going in that way, E2 and E3 are incident on V2 and V3. As we said before, E4 is incident on V5. And as far as some facts about the vertices, V1 is adjacent to itself. V1 and V5 are adjacent because they have an edge connecting them. And what else? Let's see. How about V2 and V3 are adjacent? And we mentioned before that V4 is isolated. It's still part of your graph, but it doesn't have any edges that are incident on it. Cool, cool? All right, so these are just sort of some notes about our graph. And let's go on to another definition. So a directed graph or digraph consists of two finite sets and non-empty set V of G of vertices and a set D of G of directed edges, where each is associated with an ordered pair of vertices called its endpoints. If edge E is associated with the pair VW, of vertices, then E is said to be the directed edge from V to W. So the last graph we did was not directed, okay? And I just wanted to give you a couple of examples of hubs, all right? So here, this one was kind of cool. It's the amplification audience of folk following 3 or more hashtaggers, right? So I thought that was a pretty cool one. And then here, as you can imagine, an airline hub. All right, so these here, I don't think either of these were directed per se, but these are some pictures of graphs that are in real life, right? Okay, so some more definition and notation. A simple graph is a graph that does not have any loops or parallel edges. So in a simple graph, an edge with endpoints V and W is denoted the set VW. Good so far? Okay, awesome. So for example 2, let's go ahead and draw all simple graphs with 4 vertices, U, V, W, X, and 2 edges, one of which is VW. Okay, so one of the requirements here is that one of the edges has to have V and W, right, being connected. So if I start with that premise, I can certainly do a graph that looks like this, where we've got U and V, and then V and an edge between U and V, and an edge between V and W. I can also do, let's see what else we could do. So that would be like number 1. Well, this one will be number 2. So again, I'm going to start with VW. And then what else could we do? We could do WX or XW. And now putting another one in. And again, so we need to have VW connected. And what else could we do? We could go across like this. And then there's just one more way, I believe, that this can happen. The fourth way would be like this. Cool, cool? So there's 4 possibilities when we specify that there has to be an edge between V and W. All right. So another definition here. Let n be a positive integer, a complete graph. Whoops, my colors right here. A complete graph on n vertices denoted k sub n is a simple graph with n vertices and exactly one edge connecting each pair of distinct vertices. So when you have a situation like this, well, K1, n is 1, so you're going to have how many vertices? Good, 1 vertex. And how many edges? Beautiful, 0 edges, because why? Because there's not 2 distinct vertices. So here for K1, we've just got 1 vertex, and so this is the simplest situation that we have, K1. Cool so far? All right, K2 is going to have how many vertices? Beautiful, 2. So I'll just name them vertex 1, V1, vertex 2, V2, and then we'll connect them. And that is our K2. K3 has how many vertices? Beautiful, 3. So we'll have vertex 1, vertex 2, and then I'll just have vertex 3 down here. Doesn't matter where you place them. And then we need to have a single edge connecting each vertex, so each pair of vertices. So here we go. Cool so far? That is K3. And K4. How many vertices? Awesome, 4. So we have V1, we have V2, V3, V4, and then 1 edge connecting each pair of distinct vertices. So we'll have a situation like this. And then what else? What am I missing? Did I connect every pair of vertices? No. I can crisscross them, right? Cool, cool? All right. So remember, math is all about definitions. You want to make sure that you've met the definition. So here we go, another definition. Let m and n be positive integers. A complete bipartite graph on mn vertices denoted K mn is a simple graph with distinct vertices v1, v2 down to vm and w1, w2 down to wn that satisfies the following properties. So for all k equal 1, 2 down to m, and for all j and l equal 1, 2 down to n, there is an edge from each vertex vi to wj. There is no edge from any vertex vi to vk, right? So the v's don't connect. There is no edge from any vertex wj to any other vertex wl. Okay, so now let's draw complete bipartite graphs on K22 and K24. So, here we go. K22. One easy way to do this is to make your vertices in kind of up and down in columns in a way. So there's 2 v vertices, or whatever dummy variable you choose, and there's 2 w vertices. So the w's can't connect to each other and the v's can't connect to each other. And so you end up with each of the v's connecting to each of the w's and vice versa, since they are not directed. Okay? Good so far? All right, so why don't you try to do K24 and see how you do. Go ahead, pause the movie, and then you can work it with me to see how it went. All right, let's see how K24 went. So it'll look the same for the V vertices. We'll have V1 and V2. And I'm doing K24. And so now our W vertices, we have 4 now. All right, so remember, you don't connect any of the V's or any of the W's to to no V's, the 2 V's don't connect and the 4 W's don't connect. But we will certainly have a connection going out from V1 to each of the W's or vice versa, whichever way you like thinking about it. And then the same with V2. Cool, cool? Kind of pretty, huh? All right, here we go. Another definition for us. A graph H is said to be a subgraph of a graph G if and only if every vertex in H is also a vertex in G. Every edge, in H is also an edge in G, and every edge in H has the same endpoints as it has in G. All right, another definition. Let G be a graph and V a vertex of G. The degree of V, denoted DEG parenthesis V, equals the number of edges that are incident on V. Now loops are counted twice, because if the vertex was, say, called V1 and an edge was called E1, you could write that as a directed graph as V1, E1, V1. So it's counted twice. So an edge that is a loop is counted twice. The total degree of G is the sum of the degrees of all the vertices. Of G. All right, so now let's look at this graph here, example 5. We want to find all subgraphs of the graph H illustrated below. So our subgraphs are going to be, looks kind of small, but you'll be surprised how many that we have. Let's just sort of find out some info about this graph. So this is the graph H, okay? And so what is the degree of V1? Good, you're gonna count the loop twice, and then you've also got an edge connecting V1 and V2, so it's got a degree of 3. And what about the degree of V2? Beautiful, it's just 1 because it just has one edge that's incident on it. And so what about the degree of our graph H? That's going to be 3 plus 1, which is 4. Beautiful. All right. So now let's start drawing pictures of all the subgraphs of H. All right, so let's just start simply. So the first one, we can just represent each vertex. So we've got vertex V1, right? The second one, we could say, oh, vertex V2. So those are both subgraphs of H. Well, the third one we could do would be what? We could have both of the vertices, right? So we would have V1 and V2. For number 4, we could have I don't know, it doesn't really, what order you do it in, but remember you've got that loop around V1. So we could have this loop around V1. And then continuing, we also, a subgraph of H would be what? If I connected V1 and V2, right? So if I had V1 and I had V2 and I connected those guys, and then what else? What else do you think? I could have V1, I could have V2 not connected, and then I could have the loop around V1, right? So that would be number 6. And I think we're done, right? So these would be all of our subgraphs. So I don't know, just kind of make sure that you can separate them. What do we have? There we go. So those are all the subgraphs of H. Cool, cool? All right, so there's a theorem here, theorem 10.1. The proof for this one's available in the text. I thought our time would be better spent on the example problems at this point of the semester. So if G is any graph, then the sum of the degrees of all the vertices of G equals twice the number of edges of G. Specifically, if the vertices of G are V1, V2, all the way down to Vn, where n is a non-negative integer, then the total degree of G is equal to the sum of the degree of each vertex, which is twice the number of edges. Okay, so 2 times the number of edges of G. Okay, so a corollary to that tells us that the total degree of a graph is, well, if you have 2 times some non-negative integer, what are you going to have? Beautiful. It's going to be even, because remember, 0 is an even number, because it can be written as 2 times 0. So we will, this proof is so easy because it comes from the theorem. So we will do it using the theorem because it's proved in our text. So by theorem 10.1.1, the total degree of G is equal to 2 times the number of edges of G which is an integer because the set of integers is closed under addition and multiplication. I think this would just be addition, right? So, by definition of even, or an even integer, the total degree of G is even. All right, so here we go. Our last example in this section is an example where, okay, let's check it out. In a group of 25 people, is it possible for each to shake hands with exactly 3 other people? Please explain. So, okay, if you think about the people as the vertices and the handshake as the edges, right? Let's see what would happen, right? So So the degree of each vertex would be what? Well, they have to shake hands with exactly 3 other people, right? So it would be beautiful, 3, and they're not going to shake hands with themselves. So, although some of my friends might. So now, all right, so the total degree of the graph would have to be what? You'd be multiplying the degree of each vertex, right, by the 25 vertices, right? So you'd have the degree of the graph, if this was true, would have to be 3 times 25, which is 75, which is not even. So this contradicts our corollary, right? So we would say the answer would be nope. I mean, the whole thing's the answer, but no, it's not possible because you don't get an even degree for the graph. Groovy? All right, well, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this video. And if you like what I'm doing, please subscribe.